Okay. Hello. Hello.
Yes, yes, start.
Am I audible?
Yeah,
Hello, all participants. I welcome you all in the first day of FDP in session 3, which will be taken by Dr. Varun Goel from NIT Hamirpur. And the topic is governing equations in CFD. So, first of all, is Dr. Varun is joined us?
yeah.
Okay, okay. So, welcome, Dr. Varun ji. So, first of all, I want to introduce Dr. Varun. So, it find immense pleasure to welcome Dr. Varun Goel, who has been working as Associate Professor, Department of Mechanical Engineering, NIT Hamirpur, in this FDP. Good afternoon, Varun ji.
हाँ गुड आफ्टरनून शर्मा जी
We are really thankful to him giving his valuable time to us. Before starting the lecture, I would like to introduce him. He did his bachelor degree in honors from MJP Rohilkhand University, Bareilly in 2002, then MTech from IIT Roorkee in 2004. He has done his PhD from NIT Hamirpur. He is having 16 years of teaching and research experience. His area of interests are heat transfer, hydropower, computational methods in fluid dynamics, solar energy, CFD in heat transfer, etc. He has guided 9 PhDs in these areas. He is also involved in various BST and MNRE funded projects in these fields. He is very young and dynamic scientist also. He is having more than 100 paper publication in very high impact of factor SCI and reputed journals. He is also member in some editorial boards of various reputed journals like Journal of Wind Energy, Journal of Advanced Energy Research. He is having many awards in his name, like Director's Medal for securing first position during his graduation. He also been awarded as Young Engineers for year 2011-12 by Institute of Engineers India. He is also awarded Hariom Ashram Prerit Research Award for outstanding research in renewable energy for years 2007 to 10. So this was a very brief citation about Dr. Varun. So now I request Dr. Varun to share his experience or presentation among us. Dr. Varun, over to you, sir. Please.
थैंक यू शर्मा जी
Thank you, sir.
गुड आफ्टरनून टू ऑल ऑफ यू डॉक्टर तिवारी डॉक्टर शर्मा डॉक्टर सिंह ओम प्रकाश जी आप हैं यहाँ पर
हाँ वरुण जी हैं
और कैसे हैं सर
ठीक है बहुत बढ़िया देख के अच्छा लग रहा है आपका लेक्चर सुनने के लिए आए हैं
अरे
We also welcome Dr. OP sir, OP Singh sir, because we don't know that he was here. Welcome, sir.
थैंक यू
shall I start now
Yeah.
so my talk is on governing equations. So basically this FDP is designed to, I think, cater all the aspects associated with the computational fluid dynamics. Now, if we talk of this computational fluid dynamics, prior to this, I feel that we should talk a little bit about the fluid dynamics. So if we go back and see that the solution of these fluid dynamics equations were not possible, we can say we cannot analytically solve these equations. And then with the advancement of the, you can say, a compute availability of these high speed computers, now we are able to solve these fluid dynamics equations with the help of your computers. So first of all, if we talk that how do these governing equations, what are the significance of these governing equations, then how do we can say discretize those governing equations, and then we can convert these differential or integral equation into the set of algebraic equations. And when we get those set of algebraic equations, again the problem is how to get the solution by using that algebraic equations and get the solution out of it. So that is and when we get the solution, you can say now, okay, with the help of the computers, we are able to solve these typical equations, which are not easily solved with the help of, without aid of any computational tool. Oh. So all CFD in one form or another is based on the fundamental governing equations of fluid dynamics, the continuity equation, the momentum, the energy equation, and you can say a conservation of a species. If we talk a little bit in the terms of a mass transfer aspect, then we can say we induce a conservation of a species. So these equation lead us to a basic fluid dynamics equation, and when we get those fluid dynamics equations, then our objective is to convert those equations into the, you can say, your algebraic form of that equation, then again applying certain mathematics to get the solution out of it. So if I say the fundamental physical principles upon which these equations are based, you can say a mass is conserved, Newton's second law. You can say energy is conserved. So there are certain conservation phenomena, and we know them. These are conserved in nature. So based upon this, we develop our generalized equations. So if we talk in terms of analysis approaches, there are two basic approaches by which we try to solve our problem. One we can say a Lagrangian approach, another we can say an Eulerian approach. Now, the question comes in always our mind that what is the need for doing this two kind of a different approach? Why don't we have a single approach, and based upon this we are able to find out the solution? Why we have only a single approach? Okay, we only have a single method by which we can get the solution out of it. So if I say they both serve the different purpose, if you see, you track the location of any migrating bird, you will go by a Lagrangian approach. But if you are interested in counting the birds passing a particular location, you need a Eulerian approach. So depending upon what analysis we are interested in, either we are tracking a particle, or either we are interested in what is the behavior of our fluid. A fluid flow field can be thought of as being comprised of a large number of finite-sized fluid particles which have mass, momentum, energy. Mathematical laws can then be written for each fluid particle. This is the Lagrangian description of fluid motion. कुछ कह रहे हैं?
Please mute your mic. Someone mic is unmuted. Please carry on, sir.
Yeah.
Okay. Another view of fluid motion is the Eulerian description. In the Eulerian description of fluid motion, we consider how flow property changes at a fluid element that is fixed in space and time rather than following
Hello.
individual.
Excuse me, sir. Can you display slides in full screen, sir?
Okay.
Now it is okay.
Now it's
it is
clear?
okay. Yeah.
Okay. In space and time, XYZ, rather than following individual fluid particles. So these are the basic difference of these two approaches by which we can analyze our fluid. So models of the flow choose the appropriate fundamental physical principles from the law of physics, such as mass is conserved, Newton's second law, energy is conserved. Apply these physical principles to a suitable model of the flow, and from this application extract the mathematical equations which embody such physical principles, and based upon that physical principles the equation can be now converted into certain form by which we are able to solve. So here I have shown you 4 figures. If you see a finite control volume fixed in space with the fluid moving through it, and finite control volume moving with the fluid such that the same fluid particles are always in the same control volume. Infinitesimal fluid element fixed in space with the fluid moving through it, and infinitesimal fluid element moving along a streamline with the velocity v equal to the local flow velocity at each point. So these are basically 4 models. Based upon these 4 models, you can say we are able to solve the or model our physical phenomena into a set of a mathematical equation. Now, basically, if you see all these 4 will lead to a single equation, but there is a little bit difference there. If I talk in terms of both left, if I say a finite control volume fixed in space with the fluid moving through it, and infinite fluid element fixed in space with the fluid moving through it, it will lead to me a conservation form of equations. Whether if I talk both of the right hand side models, I will get a non-conservation form of equations. But again, these conservation and non-conservation forms are interchangeable in nature. They are interchangeable. But again, depending upon the utility, or you can say whenever we talk about the flux, so they will help us ease in the writing the programs for the, if we are need in that. So depend upon that. Again, if I talk upon the finite control volume approach, by this I will obtain the equations. They are in an integral form of equations. Whether when we use these infinitesimal fluid element approach, I will get the equations that is in the differential form of the equations. Now, my question is, which one is, you can say, better, or you can say more easier to understand or more easier to program, or if being a layman, what will be your option? So it's a question for you, whether you go by the integral or you go by the differential equation. Any response?
You can write your response in the chat box. Sir, integral form. Mr. Ayush Pandey says integral form.
Integral form. Can anybody write some line about the how I will support this integral form?
Please write. Anybody having any idea? Mr. Manoj P. Mahore says integral as domain irregularities can be captured.
Okay, chaliye. Let's we'll discuss. So you can use both the methods, but again, integral form of equation generally considered to be the pure form of equation, because in the differential form of equation, there is one assumption that the function is continuous and differentiable. So if at any place a continuity or discontinuity is there, at that particular moment, our differential equation will lead to certain errors in that. So we can say, okay, integral equation, we are not bothering about that. Any discontinuity is there, that equation is valid. So normally we can say a Reynolds transport theorem, method to convert in one form of system into the another. So that is a Reynolds transport theorem. So if you say an interpretation of that, a time rate of change of the property is equal to the term 1 plus term 2, the time rate of change of that property B of the control volume plus the net flux of B out of the control volume by mass crossing the control cell. It means the net rate of change of any system in that particular property in the system will be depending upon the time rate of change and the net flux which will crossing the, you can say, your control surface. So we come to the conservation of mass. So here just I have written them in 2-3 different coordinate system, that is just to that we can, how we can apply for a cylindrical surface, how we can apply these particular set of equations for the, you can say for spherical system, or you can say for the Cartesian system. So if you see we can say del rho by del t plus del dot rho v, that is equal to 0. That is, we can derive here that continuity equation, net mass flow out of control volume through the surface, that is the time rate of decrease of mass inside the control volume. Whatever the mass is really coming out from the control volume, that is equal to the time rate of change in the mass inside the control volume. So for different models, we are having the different representation of these equations. That net mass flow out of control volume through surface S, that is the time rate of decrease of a mass inside the control volume, which is del by del t of a volume integral of rho dv plus surface integral of rho v dot ds, that is equal to 0. That is again, these equations are more or less the same thing, but they are written in a different. So you can say one is integral form, a conservation form. Another, if you say a integral form which is in a non-conservation form, which is a del by del t, you can say a total derivative, time derivative of the volume integral rho dv, that is equal to 0. It means a net rate of change in the mass is equal to 0. Then we have a conservation form is del rho by del t plus del dot rho v equal to 0 in a differential form, a conservation form. Then we can say a del rho by del t plus rho del dot v equal to 0, which is in the differential form. We can convert them into by doing certain manipulations in the terms, and we are able to get these equations. Now, depending upon our choice, we can program these particular equations. So if you write to del rho by del t, you can simply add up all these components, and you can say all these changes are equal to 0. Then we get this particular type of equation, which is a del rho by del t plus del dot rho v equal to 0. If we go by the change in the delta mass, then the total derivative for this change in the delta m will lead to this capital del rho by del t. So this is how we can derive these generalized equations in the, you can say, continuity equations. So we have represented them in 4 forms for the different models as it is depending upon the, you can see a control volume, fixed or moving, or a small element, infinite small element, that is fixed or moving. So based upon that, we are in the position to find out these equations. And again, when we are interested to get those equations to be solved, we will use them as per the requirement of this. Now, a momentum equation. Just a minute. So now the momentum equation, that is, again, we have to now come up with the forces, all type of forces which are acting on a surface, which is equal to the net rate of change in the rho dv by dt equal to change in the force. So now we have a body force, surface forces, other forces, you can say them, maybe they act as any source for that. Let's suppose some magnetism is there, then we have some electric current over there, EMF is there, any other kind of a force which is acting here, that can also take in place in this particular type of equation. So the force which are acting over the surfaces, they are called as the surface forces, and the forces which are acting over the body are called as the body forces. So we know the gravity is the body force. You can say pressure, you can say your stresses, other forces depending upon their magnitude, whether they are acting on a body or a volumetric base. So we can say accordingly we have to take care. Sometimes there might be no any source term is there, any other force, so we can neglect this F others. So we can say now we are in the position to get this. Again, we can obtain these equations, or you can say momentum equations, again depending upon the conservation form or non-conservation form. Again, we have these momentum equation. But in this momentum equation, our left-hand side will be changed, but right-hand side remains constant always, because that is the summation of all the forces which remains the same. But again, the left-hand side, for depending upon the different orientation, the value of this changes. So you can say a linear momentum equations, you can say a Cauchy equation provide the equation of motion for the fluid known where the stress attached by the stress tensor sigma ij. Now the question is, when we have this representation of terms, when you say we are having a pressure forces, we are having a stress component in that. Now this particular component will lead to 10 unknowns. If you see the 6 stress component with the density and the 3 velocity independent components, and still we have only 4 equations, 3 momentum equations and 1 continuity equation. So that is, you can say we cannot solve, because ultimately we need 4 equations, then 4 variables, then we can solve it. So this equation is not very useful for us. We cannot get any outcome from this particular equation. So the constitutive equations provide the missing link between the rate of deformation and the resulting stress in the fluid. Now we have to make certain assumptions. Now we have to try to solve it, so that we are in the position to get it solved for, or we make a term that we have a n number of variables, then we have a n number of equations. Now we are in the position that we are able to solve and we get the solutions out of it. Otherwise it is very difficult for us to solve, because we are having 10 unknowns with the 4 number of equations. So the Navier-Stokes equation, by considering the Hookean elasticity, Stokes' 3 postulates, again something is given by the Navier's, some postulates given by the Stokes, which give us certain simplification of the equations. And when we simplify these equations, we are able to get certain form, and this form is now able to solve with the help of these fluid dynamics equations. So the fluid is continuous and stress tensor is almost linear function of strain rate. So now we can talk about Newtonian fluids. Fluid is isotropic, properties are independent of direction. When the strain rates are zero, the deformation law must reduce to hydrostatic pressure condition. So all these can be combined and can be written in single general constitutive equations. So sigma ij equal to minus p delta ij plus mu del ui del xj plus del uj upon del xi. You can say basically it is a mu del u by del y term. So it will show a linear kind of a, you can say, your Newton fluid, which is a Newtonian fluid. So it is, you can say, a shear stress tau equal to mu del u by del y. So that is a representation in terms of like this. Then we have a delta ij lambda divergence of v, which is a taking care of the Kronecker delta. That is a simplification in writing down the equations. There are also many fluids which do not behave as Newtonian fluid. You can see them non-Newtonian fluids and have different constitutive equations. Then Stokes pointed out that the sum of three normal stress is tensor invariant and defined the mechanical pressure. Average compression stress in the element is 1/3 of that sum. It means the mean deforming pressure in viscous fluid flow is not equal to thermodynamic pressure. So the Stokes hypothesis is lambda equal to minus 2/3 mu, which again help us in making this equation more simplified. And again, when we talk about the incompressible fluid, which is a divergence of V, that is equal to 0. So now the terms will tending towards only to the term pressure. So that will help us in getting this. The momentum equation for general linear viscous fluid is now obtained by substituting the stress relations. And we can say them in expanded form that rho del u by del t equal to rho gx minus del p by del x plus del by del x 2 mu del u by del x plus lambda divergence v plus del by del y mu del u by del y plus del u by del x plus del z by del z mu del u by del x plus del u by del z. So this is for the in the x direction. Similarly, we can write it for the y direction. Similarly, we can write it for the z direction. So we get the 3 set of equations for that. And now we are having these 4 equations. 1, we have the continuity equation, and 3, we have the, you can say, your momentum equations. Again, depending upon if we say the fluid is incompressible in nature, then you can say the rho del u by del t equal to rho gx. Again, if we see a acceleration due to gravity in x direction is 0, so minus del p by del x plus mu del square u by del x square plus del square u by del y square plus del square u by del z square. So you can say now you are compressing these equations, and this will help us in getting the solution more easily. Now this is just a simple representation of the equation in the polar coordinates, that we are interested to solve a problem in a polar system or a pipe case. At that time we are able to solve it. So that is the rate of stress tensor. Then we can get here in the component ur, u theta and uz. These are the 3 components. Then we have the continuity equation for the polar coordinates, and with the help of these set of equations, we are able to apply these equations in a polar system. Now again, we can use it for the spherical system. So now the energy equation. So that is a rate of change of energy inside fluid element, that is equal to net flux of heat into element plus rate of work done on element due to body and surface forces. So now the rate of change of energy inside fluid element, and that energy in the form of, either you can see them represent in terms of enthalpy or internal energy, whatever. That the net flux of heat, that is in, you can represent that in terms of temperature. So again, when we induce this energy equation, this will lead to again one term, that is, you can say, your temperature. So equation is adding 1, but again the variable is adding 1. So if sometimes we are not interested in the thermal analysis, or you can say a temperature based on energy analysis, we can use this fluid dynamics set of equation for the continuity and the momentum only. But when we try to include this energy aspect also, so then we can say we are dealing with the temperature and the rate of work done on element due to body and surface forces. What amount of work is done with the help of these forces. If I talk in terms of your shear stresses, then you can say that amount of work done obtained by that. So now you have these internal energy or enthalpy. If you represent it like this, we have that heat flux. If I say a q dot x is entering, then the q dot x plus del qx upon del x into dx is leaving out from that particular surface. So now you can say entering and leaving, and when we balance all of it in all the 3 directions, then we can say, okay, now we add up all these and the resultant is equal to your energy equations. So net rate of work done by pressure is, you can see in terms of pressure, in terms of shear. So we can say work done by forces, it is again a del up upon del x, u tau xx, tau yx, and tau zx. So they will represent the force. These are the work done by the forces in the x direction. Similarly, in the y direction. So similarly, we can say a del x of up, vp, that is the u, the velocity in the x direction, y direction, and z direction. Then we have tau xx, tau yx, tau zx. Then the multiplication with the u. Then we have a tau xy, tau yy, tau zx. So similarly, we have these components of, you can say, force work done obtained by these forces. Then we have the net flux of heat into the element. Then you can say your qx. And if you talk in terms of qx, then from the Fourier law, you can say k dt by dx. When you say del x of qx, it means del by del x of k dt by dx. And if my k is not a function of the, you can say k is not a function of temperature, so you can say your k del square t by del x square. Otherwise, we can write down del by del x of k dt by dx plus del by del y of k dt by dy plus del by del z k dt by dz. So now we have these all heat flux which are entering. If now the rate of change of energy inside fluid element, that is again some velocity, the element which is moving, it is having some internal component of its energy and the kinetic component or a potential component. So if we see a rho del by del t of E plus V square by 2, that is the velocity component, and that E, which again can be represented in terms of temperature only. So that's, it means if you go on expanding these terms, so these terms will give you that we know we all have done something for this shear components, because now we represent these shear stresses in terms of a Newtonian fluid. So they are becoming a function of mu and the velocity gradient, mu del u by del y, if I saw. So with the help of this, we are able to find out there. Again, these equations will only lead to one more variable, that is the temperature, which is not considered in the, which is not there in the continuity and the momentum equations. So that is, you can say, or so if you go on rate of change of energy inside a fluid element, that is equal to the net flux of heat plus the work done by this, and with this equation you can say this is your generalized energy equation. So that is rho total derivative of del by del t E plus V square by 2 equal to minus del up by del x plus del Vp by del y plus del Wp upon del z plus del u tau xs upon del x. So go on expanding these terms. Again, we do certain assumptions by considering that, okay, k is an isotropic again, so it is, otherwise it is kx, ky, kz. So we consider it to be isotropic, so it is k. Again, when k is not a function of temperature, so k comes out and it is simply written as a Laplace equation, del square t by del x square plus del square t by del y square plus del square t by del. Again, depending upon our physical problems, we can derive more simplified form of these equations. Otherwise, these generalized equation of these fives are quite complicated and quite big, and these are the nonlinear set of equations. As we have seen in the momentum, if we don't assume any approximation for the stress component, we are not able to move ahead in the terms of solution. So we have to come out with a certain approximations, and these approximations will lead to these equations to the Navier-Stokes equation. Now, depending upon those, we have to go to the solution of these Navier-Stokes equation, again depending upon our physical problem. So these are the just representation of some terms which you can write down. If you represent a rho del u by del t, rho del v by dt, rho del w by del t, rho de by dt. So basically it just tells you, if you change simply in the parameter u, v, w, e, the rest organization of the equation remains same. So one more type of equation, that is a conservation of species. And in this, which is quite useful when we are dealing with the species. So consider the control volume. Species may be transported by advection with the mean velocity of the mixture and by diffusion related to the mean motion in each of the ordinate directions. So these are the advection and the diffusion of all these. Let's suppose a species, if we talk in terms of these gases, a mixture of carbon dioxide, mixture of gases, and we are interested in analyzing these, their diffusion of these concentration of the different gases, or sometimes their chemical reactions. At that time, we are interested in getting this generalized equation and to analyze these equations also in corresponding to those equations which we have studied. So the net rate at which species A enters the control volume due to advection in the x direction is this much, and molecular weight of a species to evaluate the diffusion flux. So normally these equations are normally represented in terms of their molar volume or per unit molecular weight, so that they will give us a quite uniformity in the by mass conservation. So you can say there u del rho a by del x plus v del rho a by del y, that is DAB, that is a diffusivity, or you can say write them in terms of their molar form. So again, we have this simple representation of the equation. If we represent these equations in 4 terms, which you can say unsteady, advection, diffusion, and source, and you try to make them, okay, how the equation will look like, or do these equations are easy to remember? So that is the unsteady term. It is a del rho by del t for the continuity, the momentum del u by del t, del v by del t, del w by del t. Then we have this advection term. In continuity, we don't have a diffusion, but in source, we have nothing. But in, you can say in diffusion, all these Laplace sort of formation, del square u by del x square plus this, that represent the diffusion. And again, some external things. It means source, here you can say your 1 upon rho del P by del X. But again, we are having any other source which is there. Let anybody is there. If we are studying the flow of fluid over any surface and somebody is standing over there to disturb the fluid, basically that is act as a source. If anybody is moving a rod there, these type of things we have to take care, and these will act as a source. And these are the source which are basically now changing the pattern of your fluid flow. So this energy equations, conservation of species, by this you can represent your term. So unsteady flow in one with all the condition at any point are called as source term. Example, pressure, electric, gravitational, magnetic shear, etc. So advection occurs by the external force, diffusion by the concentration or by any gradient. So just a minute, I will show you the continuation of this. That is, how do we come out with the, you can say, now how do we convert these governing equations into the, you can say, your algebraic form. Now we know what is fluid dynamics, then we know these generalized equations. Now the thing is, how do we get those generalized equation into algebraic form, from where the computational part start? So normally 3 methods for study of flow phenomena. Commonly they are analytical, experimental, and computational. So शर्मा जी, अभी आधा घंटा तो कोई दिक्कत नहीं है ना?
हाँ जी, हेलो. हाँ, no problem, sir. No problem.
So the analytical method is a generic process combining the power of the scientific method with the use of formal process to solve some type of problem. Accurate results for dependent variable as a continuous function of space and time dimension. Limited solutions are available. So basically, analytical solution is very good. We even need them, they are accurate, but again, the problem is they're limited solutions. Experimental, always useful, but they are costly. So is computational becoming prominent with development in hardware, results at discrete point, large number of points can be taken. Results depend on accuracy of model, difficulties in modeling. So these partial differential equations applicable continuously for all the points in the domain needs to be converted to difference equations applicable at discrete points within the domain. So in this presentation, we will try to discuss about the discretization. Now let's suppose we are having any differential equations, and our objective is to convert that generalized governing equation into a set of algebraic equations so that these equations can be solved. Now that is what a CFD is, a computational fluid dynamics. How do we make it easy in terms of doing computation with the help of these equations? So let's suppose we are having this, you can say a point, you can say a nodal point, which you can represent it by a ij, and we are basically clustering. Let's suppose we are having this particular as a physical system, and we are interested to get the solution for this particular physical system. So what we do, we try to make them discrete points. Let me make certain discrete points, and over these discrete points we are able to solve our equation, and we will get the solution for these discretized points. Yes, there is a problem, because if we say how do we connect these point to this point, definitely will, you can say we are not getting, they will not vary linearly. If I join them linearly, they will not, I think they might be non-linear in nature. So you can say for that we can choose them, these points, depending upon my requirement of the grid. So the conversion of partial derivative into difference quotient is based upon the Taylor series expansion. And if I say that fx plus dx, and that is the exact expression for x plus dx, is fx plus del f by del x into delta x plus del square f upon del x square into delta x square upon factorial. So if you see, we are having a, but it is not limited here, it is up to infinite. So it is the exact representation of the fx plus dx. But the question is, if we go on considering the all element, then we are not able to discretize it. But if you see, if your delta x tending towards very less amount, so your series starts converging if your delta x tending towards the 0. But if your delta x starting tending towards a very higher value, your series will never converge. So that is one limitation, that is your delta x should be tending towards 0 to get the series to become convergent. So if you simply represent a term that you are interested in finding out the value at fx plus delta x at this particular point, that must be equal to fx, that is this point, plus the differential of the term at this particular point multiplied by the delta x, plus double derivative of that into delta x square by factorial 2 at this particular. So you can easily find out this value if you know the value at this particular point. So if you simply say, okay, ui plus 1j, if I simply represent these terms into I and j, or I plus 1j, I minus 1j, ij plus 1, and ij minus 1. If I say simply that it is my ij and it is I plus 1j, ij minus 1, ij plus 1, and I minus 1j. So I simply, if I am to evaluate these values, I can use the Taylor series. I can say that ui plus 1j equal to uij plus del u by del x ij into delta x plus del square u by del x square ij to delta x square upon factorial 2 plus del cube u by del x square. And this equation is going on. Now let's suppose I am interested in calculating a first derivative, simple del u by del x. That I am interested in calculating this value, del u by del x. So this del u by del x is equal to ui plus 1j minus uij divided by delta x. If I address terms, del square u by del x square delta x by 2 minus del cube u by del x cube ij delta x square upon 6, that is factorial 3, and so on. So if I say my del u by del x, that is nearly equal to ui plus 1j minus uij upon delta x. It means when I go on considering this, I am introducing certain error here now, because del u by del x is approximately equal to this. It is not equal to this. It is basically equal to, these terms are also there. So we have to take care of, so again, so we have to choose at the order of error. If my delta x is very less, okay, if it is, I say nearly tending towards 0, very less, okay, you can say it is very close to this value, But if my delta x is quite large, then this value is similarly, if we are interested in a negative side, or you can say a notation on right side and left side, and if I simply say that this is a on the left side, that is a I minus 1j on this side. Any doubt?
Hello. Please carry on.
शर्मा जी कोई
नहीं
दिक्कत?
sir, please carry on sir.
No, no.
No problem.
Yeah.
If this is negative delta है,
Please. Please mute your mic. Participant, please mute your mic.
so we can say a ui minus 1j that is equal to uij minus del u by del x ij delta x plus del square u by del x square ij del x square upon factorial 2 minus del cube u by del x cube. So now if I'm interested in del u by del x, I can say uij minus ui minus 1j upon delta x plus this. Now I simply writing these, they are equal, but again there is a certain terms which induce error in this kind of a discretization. But again it depends upon our selection of this. You can say that it will depend upon our this delta x. If my delta x is really tending towards 0, very small, then this error is very less. Now if you add both the equations 1 and 2, so then you get this uij plus 1j minus ui minus 1j equal to 2 times del u by del x ij delta x plus del cube u. So here one term, that is a del square u by del x square, is now eliminated from the equation. And now you see the term O delta x square. Initially it is in terms of a delta x. So we can conclude that the order of error there is delta x, but here it is delta x square. So it is little bit more accurate on going through this. So depending upon their equations, they are called as a forward difference, they are called as a backward difference, and these are called as a central difference. So with the help of this, you are able to find it out the first order derivative. Similarly, if we are interested to obtain the solution for a higher accuracy, we can go by a polynomial approach. We can fix the values, and based upon this, we are in there to find out these ABCs. And when we find out these ABCs, but again, these terms will induce more terms, U1, U2, U3, as we are getting only 2 terms. So with the help of these, increase in the accuracy, completely, you can say your other part when you try to solve these equations. Now, the second order derivative for this. So for this, del square u by del x square ij, you can say ui plus 1j. Let's suppose when we talk about this, we have this I plus 1. We are interested in this value. So what we can do? We can cancel this term. So what we do? We can simply add them, so that it becomes a 2. So it becomes 2, and this becomes ui plus 1j. That will become a ui minus 1j. So you can say ui plus 1j plus ui minus 1j. and that is equal to your 2 times uij divided by delta x square, and the error is here, it is of second order. Now you can say with the help of this, you are able to get this second order derivative, which will help us in getting your differential equations or generalized equations into converting that in terms of these points. You can say your whole equation can now be written as uij plus 1, uij, ui minus 1j, uij minus 1i plus 1j. Similarly, you can say vij plus 1, vij, vi plus 1j, vij minus 1. Similarly, your pressure, your density, and your temperature. If there is a 3 dimension, you can say I, j, and k. So it is uijk or ij plus 1k, like this. So your whole parameters will now denoted at these nodal points and the values assigned here. If you want to increase the accuracy in the second order, you will see that how much complications in this particular equation. But again, it will lead to the fourth order accuracy. So ultimately, complications involved, accuracy improved. But again, we have to be very much conscious that we are able to solve them, because ultimately we don't know these values. We will iteratively solve these values. Do our procedure will lead to the achievement in this particular solution or not? So we cannot make our set of these discretization to be very much complicated, otherwise it will lead to problem in the CFD techniques, which will help us to obtain the solutions. Because when we get these discretization, then we can say we study the CFD techniques. So let me have a simple example of a 1D unsteady heat conduction heat equation, del T by del T equal to alpha del square T by del x square. Now you simply see a del T by del T, that is T j n plus 1. So here you see one more term, that is T temperature is varying with respect to time. So that we are representing here at the superscript. So subscript is for dimensional things, x, y, z. And here this n plus 1 is denoting your time. So the variation in the dt over dt, that is t at n plus 1 minus t at n divided by delta t. So that is the discretization of this del t by del t, now equal to alpha del square t by del x square. Now this del square t by del x square is again at any level n, t j, tj minus 1 and tj plus 1. You can say tj plus 1 plus tj minus 1 minus 2tj at n divided by delta x square, plus this is my error term, that in time domain it is the order of delta t, and in the order of delta x is the order of delta x square. Now that is all. We can have a difference equations or algebraic equations now we have. So it is the finite difference equation that is actually solved instead of partial differential equations. But again, before solving, we need to examine it for some desired properties, that you can say a consistent, or you can say there is a stability, and there are many more terms which will help us you to get out of any, otherwise your solution is converging or not. That is what a main thing is. So convergence. Convergence, generally a consistent stable scheme is convergent, and convergence here means that the solution to FD approaches the true solution to the PD having the same initial and boundary condition as the mesh is refined. So we can do a error analysis. You can say how many sources of error which are introduced. So if you have seen one error we have introduced already, that is your discretization error. The difference between the exact analysis solution of and the exact solution of the corresponding difference equation. And the second type of error is the rounding off error, which is introduced in calculations. When we have certain values, we make it certain rounding off, and this rounding off will lead to your error inside the results. Now, sometimes your solution becomes starting diverging. And at that time, it is very difficult for us to see what is going on. We are not able to get the solutions of it. My solution, which is need to be converged, it is now going to diverge. It means your error is increasing iteration by iteration, and the magnitude of these errors, both the errors, is so enormous that we are not able to get any converged solution. So we can have this, you can say the discretization and rounding of error, and with that you can satisfy a certain equations. And when we write down this in terms of epsilon, which is the error, so now I can say this particular equation is to be satisfied, which is basically an equation in general terms of temperature. And this particular equation should also be satisfied with the error. And if error is already present at some stage, then the solution will be stable. If error is not growing, error is reducing. It means epsilon I at n plus 1 should be less than epsilon I at nth. And that is what, this can also be represented with the help of the Fourier analysis. And we can now say, based upon that, we get certain criteria which restrict our, you can say, your time step or your dimensional delta x. So if you keep your alpha delta t upon delta x square should be less than equal to 1/2 for a 1D heat conduction problem, then you can say your solution will converge. And if your delta t is greater than that, then it means your solution will not converge. Or we have to choose another method. We can say, okay, we can go by the implicit approach, because till now what we are doing basically at this time level n plus 1, and rest solutions are at time level n. It means we are marching towards the time at n plus 1 level when we are having at a time level n. So again, we have to choose the scheme depending upon our solution method, that which equation is, which method or which scheme is desired for such kind of a scheme. So you have now two solutions. If you see simple thing, that whether you are interested in going these here, you know these three values, and you try to obtain this one value. And either you write your scheme depending upon three unknown and you know the one values. That is what the difference in the explicit and implicit schemes. If you know all these three values, they are called as the explicit, and you are marching in the time direction. You know all the values at time t n, but you don't know the value at the single value at n plus 1. So you know this three. With the help of these three, you can calculate this. With the help of this, you can calculate this. With the help of this, you can calculate this. And like on, you will calculate all the solution at the n plus 1 level. And further at the n plus 2, you know all the values at here. You can go on increasing. So similarly, you will march in the time directions. But in the implicit scheme, your equations are written in such a fashion that there are these three unknowns and you know only one values. So I have seen this. There is a one special method by which you can solve, and that is your implicit approach. So it will help you in analyzing according to sorry. So you have both the things. You are having, you can march in that direction, but again choosing upon the delta t time step. That is explicit approach. Again, you have that implicit approach, in that you have to simultaneously evaluate all the values. And when you have to evaluate this simultaneously, that you need a matrix inversion sort of thing. It means you need a more heavy program, and it will lead to more computational time. But again, your solution is independent of time in the implicit scheme. So some schemes, though this in explicit, there are some advantages, and in implicit, there are some advantages. So depending upon you, if you have to obtain only temperature for 10 seconds or 20 seconds, better to go by explicit. But if you need for 2 or 3 hours, do that. So accordingly, we have to choose all kind of things, because I will not discuss these implicit because there is one special session on this particular topic. So that's all from my side. Now, any question?
If anybody is having any doubt, you can write in the chat box. Any one of you, dear participant, please write some problem. Any query?
Sarmaji, no query at all. Please close the session.
One query is there, Mr. Amit Kumar. Difference between round off and truncation error approach.
Kindly explain about implicit and explicit approach. Okay.
Two queries is there. First is from Amit Kumar. Difference between round off and truncation error. And second one is Sukanta Nayak. Kindly explain again about implicit and explicit approach.
So implicit and explicit first of all, then we will go through. So if you see here, this equation is Tin plus 1. If I go on here, this Tin plus 1 minus Tin for this particular equation. Let me have this equation d capital del T by del T equal to alpha del square T by del X square. Now, when we have this kind of a term, you can say, now your time is at Tin plus 1, because when you are in dg by dt, so time level at a one step ahead, that is a n plus 1, minus Tin upon delta t, that is a alpha upon delta x square Ti plus 1 n minus 2 Ti plus Ti minus 1 into at n. Now if you see, if I replace this n with the n plus 1, let's say Tin plus 1 minus Tin divided by delta t equal to alpha delta x squared Ti plus 1 n plus 1 minus 2 Ti n plus 1 plus Ti minus 1 n plus 1. I can write any one, either for the next time step or the previous time step. So now when you see here, so in this particular case, if I talk of explicit one, because I am having Ti plus 1, Ti minus 1, so at nth level, this is my nth level, and I am moving towards n plus 1, and I am getting this value. So if I am interested in Ti at n plus 1th level for this Ti's, so it means I know all these three values, and with the help of these three values, I can obtain the solution for the T3 at n plus 1 level. And similarly, when I go on increasing these values, I can obtain 2, 3, 4, 5, 6, 7. When my T'th at n plus 1 is over, I can move towards the n plus 2 level. Now, when we talk about the implicit approach, In this, what we have to do? We are having all these values are at n plus 1th level. N plus 1, n plus 1, n plus 1, and this is n plus 1, the same thing. And we are only having a known, that is tin. So we know only this single value, but we don't know all these three values. So with the help of this, we are trying to calculate the value of, you can say, with the help of only one known, we are not able to find out this. Now, similarly for this 3, with 1 you cannot get 3. We know this, we cannot get this 3. With this 3 we cannot get this, and similarly we cannot get this. So now we have to simultaneously solve these equations. And when we have to simultaneously solve these equations, we can say we have to solve with a certain, in which you can say a matrix problem. But in the explicit, we know these 3 values, and with the help of this we can get the 1 value. So this is the difference here. So I think.
So is it clear to Sukant Naik? So, okay, one more question is, which software can be used for error analysis?
Which software can be used for?
It has been asked by Fanindra Mishra.
Basically, for which type of error? They are basically interested in the uncertainty of anything, or?
Hello?
Yes.
Sir, how to use the error analysis in softwares? Which software can be used for error analysis?
Means this kind of error what we have evaluated today.
Please write which kind of error you want to remove.
Otherwise, for
measure.
these CFD, you can use the ANSYS, OpenFOAM. There are a lot of many software, Star, TD. और आपका एक सेशन है पूरा जो उसमें ये TDMA के ऊपर जो बात करेंगे इसके ऊपर implicit, इसलिए मैंने इसको कवर नहीं किया.
There is a separate session. There is a separate session.
तो जो TDMA के ऊपर बात करेंगे.
Yeah.
तिवारी जी, मेरी एक मीटिंग है, मैं निकलूं क्या?
Okay,
yes,
okay.
Just Sharma, please
okay.
Close.
Yes. So thank you, Dr. Varun. Thank you very much for such a wonderful and informative lecture on governing equation fluid dynamics. In this lecture, he discussed about fundamental equations of fluid dynamics, analysis approaches very well. He explains different models of the flow. Either we can go integral or differential approach as per the problem formulation. He covered basics and usefulness of continuity equation, momentum equation, Navier-Stokes equations, conservation of species. He discussed the need for numerical methods, analytical, experimental, or computational. So thank you, Dr. Varunji. Thank you so much for such a nice talk. Now I would like to invite our mentor and source of motivation to us, Professor Arun Mittal sir, Mechanical Department, to please join for vote of thanks to Dr. Varun. Sir, over to you, Mittal sir.
Okay. Hello.
Yes, you are audible, sir. You are audible, sir.
Yeah.
Okay. So I, on behalf of Mechanical Engineering Department, extend my own behalf, extend a very hearty vote of thanks to Dr. Varun. Thank you for sharing his views and giving some time. Thank you. Thanks a lot.
Thank you.
Thank you, sir. Thank you so much, sir.
Okay, thank you, Dr. Varun.
Okay. So, dear participants, a link has been sent to you. You fill that link. We have got the 80 responses till now. So you go through it fast because we have to close this link earlier. And the participants who have filled the form, they can leave.